Good evening. As the President of Hong Kong Dental Association, I'm pleased to be here to introduce our speaker, Dr. Eric C., for the lecture on how air filtration technologies can prevent you from infections. Wearing face masks has become a basic personal protective equipment to prevent the spread of COVID-19 pandemic. Traditional air filtration, including surgical face masks and high efficiency particulate air HEPA, filtered in air conditioning and designed to trap and block small particulates and microorganisms through sealing, interception, inertial impression, and diffusion. One of the drawbacks of the traditional air filtration technologies is the saturation of microbials over time, leading to biofouling effect. Some filters would just add biocides or disinfecting agent to reduce the microbial level, which may introduce other side effects. In this talk, Dr. C would provide a brief introduction to different technologies used in air filtration and their pros and cons. Besides, Dr. C will introduce the latest research in a highly positively polar polymeric coat membrane in air filtration, which can not only arrest 99.9% of microbial, but also effectively activate a variety of pathogen, bacteria, and virus, including CoSAR-2. Dr. Eric C. is an associate professor of the Department of Science, Hong Kong Metropolitan University. He is also an adjunct professor in the Department of Chemistry, the Chinese University of Hong Kong. He is a toxicologist and chemist with one of his research interests in applying antipathogenic material in air filtration technology. He also involved in developing the first oral vaccine for COVID-19 by the use of recombinant Bacillus subtilis spore. Dr. C actively participated in different media to explain how to choose different antimicrobial agents, face masks, and rapid antigen test kit during the COVID-19 outbreak. I now invite Dr. C to deliver his lecture. Members who have questions may put forward those questions at the Q&A session after Dr. C's presentation. Dr. C, please.
Thank you very much for Dr. Nelson Wong for his introductions. Okay, I switch to my presentations. Okay, you can see my PowerPoint. And today, what I will try to do, okay, I just hear Dr. Weller's presentations, and I got some slides changes because he touched some of the slides about the face mask, okay. But anyway, it's fine for me. That I would try to use 45 minutes to discuss about some new air filtration technologies. First of all, before we try to know the air filtration technology, we need to understand the virus, bacteria, and all other pathogens that we deal with every day. Like the virus, okay, virus is the smallest entity that in the in this kind of particles, okay, and it's small, okay, around 20 to 400 nanometers. And for COVID, it's a bit in the middle, so it's around 100 microns in size. And then larger than that, it will be the bacteria in around micron size. And then we will have some particulates and then pollens. Okay, that's the range, that's the spectrum that we like to screen off by the use of air filtration. No matter we talk about the air, the face mask, or the air filtrations by the air conditioning systems. And for COVID-19, the virus, okay, that's something you need to understand. First of all, the size of it is around 0.1 micron, which is very small. And it's smaller than the most aerosols that we generate. Okay, I will talk about the aerosol size later on, but it's much, much smaller. So every aerosol will contain quite a number of virus, COVID-19 virus. And the second one I would like to highlight is the COVID-19 virus is a negative charge, okay, when they are in the pH range, okay. Why is it so important? You will see how effective is the conventional filtration tools that we use, okay, later on. And the third one is the normally when it's in an aerosol situations, the COVID-19 virus can survive in around 3 hours, whereas the half-life in the aerosols is around 1 hour. So every hour they will reduce by half, and around 3 hours in the aerosol, it will die all of it. But when they are deposited on some surfaces that with the supply of like humidity or other kind of favorable situation, they will survive a longer time. And then usually when we talk about the infections, we are not trying to infect directly by the virus. Okay, we usually try to inhale, or we through the contact, we will touch some of the aerosols. Okay, and most of the breathable aerosols we talk about is something that's below 10 microns. Okay, and in the size of, I can't use the annotations. And no matter we breathe or we talk or we try to coughing or sneezing, okay, we will generate aerosol. And quite surprisingly, okay, some of the research telling us that no matter we breathe, we speak, we talk about something, or we cough, the amount of small size aerosols are more or less the same. Okay, the size, in terms of numbers, the number of aerosols we generate are more or less the same. So it's the same. People's coughing or people's trying to speak or trying to breathing, they would exhale the same amount of aerosols in small size that we can breathe. If we try to take a look onto some extreme situations like people sneezing or coughing, okay, they would generate aerosols and propagate in a longer distance. And when they are sneezing, we talk about the length is more than 6 meters. Okay, you can still see some of the dots beyond 6 meters. But most of the large droplets would be deposited onto the ground in a shorter distance, whereas those smaller in size, okay, the aerosols will be propagated to a longer distance. Okay, for coughing, the case is not as severe than that of sneezing. It will be at around beyond 2 meters, around 3 to 4 meters in length, okay, in average. And when we talk about when we just doing our normal breathing, the length of the exhale is around 1 meter. So the government's campaign by using social distancing actually work, okay, but it's talking about it works when we breathe, okay. We don't try to do coughing or sneezing, okay. If we try sneezing or coughing, we need to, when we find some people sneezing, then we have to escape a further distance so as to avoid to have a high chance of infections. Okay, and one point is very important, that this graph is talking about some people that didn't wear any mask. Okay, so if we wear some mask, the situation will change. What if people who wear a mask? Okay, here is the scenario. Okay, when the people who did nothing and just coughing, and he expelled some of the aerosols and also the large droplets from his mouth, and you can see the density is like in the diagram A, okay, without any mask. But if he try to wearing a not ordinary surgical mask, the situation already changed a lot. The density of the aerosol and also large droplet will try to trap by the face mask, and only a portion of it will be released. But how about if we try to wearing N95? It's even better, because the N95 or similar level of mask will try to block 95% of the aerosols escape out from your mask. So only 5%. So you will see the density of the large droplet will be much smaller. But I understand that for dentists, okay, I'm not dentist, but I understand that most of the time you are facing your patients, okay, and what if they didn't wear a mask and you wear a mask in front of them? What would happen? Okay, here are the scenario you can take a look. Okay, those patients, okay, or infected persons, okay, without a mask would try to provide same amount of aerosols and large droplets, okay, if we have a distance like 1 meter, okay, and no matter what kind of mask you're wearing, okay, the density of the droplet and aerosol would be the same, because your opponent, the patients, didn't wear a mask. And so that would be the highest chance that you will get infected if you are not wearing a mask properly, or you choose a wrong mask, okay? So from the first few slides, I already told you that wearing a mask is very important, okay, especially as a practitioner of a dentist. So how the current technology, okay, how can they protect you from being infected? Okay, let's see what's the geometry, or what's it look like for our face mask. Okay, for face masks, the core material is called the membrane material. Okay, we call it 溶噴布. Okay, and I remember that 2 years ago that the membrane material is quite expensive, because we don't have much companies supplying it, and there's a surge of membrane materials. Okay, and I can hear some of the manufacturers, they tell me that at that time they need the highest price of the membrane material is around a $1 million for a ton of membrane material. Okay, a ton of material can make around 800,000 pieces. Okay, so it's around just the membrane material without the other components and without the process, it already charged you $1.5. Okay, Hong Kong dollars. And so it make up of some non-woven microfiber. Okay, the material you use is the same as the environmental bag you're wearing every day. Okay, you go to markets, you have the environmental bag, and that material are the same as the membrane material, but they try to fabricate it like in this diagram. Okay, in these photos, it's just like some fibers, and those fibers with the diameters of 2 microns, and the distance between them is around 20 microns. Okay, you might ask the questions. The distance between them is 20 microns, and the droplet we would like to trap is in microns. Like the aerosols we try to we facing every day is around 4 to 8 microns. So it's a bit large when we talk about when we considering that the whole size of the membrane material. How come it can trap? Okay, you can see from this bar chart that when we just use ordinary membrane material without any properties, it can only trap around 36% of the aerosols or particles. But what if it can achieve 99% like the face mask we buy it in the markets? It's add something else. Okay, what they add is the electrostatic charging. Okay, they would apply a high voltage to the membrane material to make it charge, and the electrostatic charges is a negative charge particles. Okay, so so you might think about when we go back to your first slides before, I've told you that the COVID-19 virus is actually a negative charge virus in neutral solutions. In an aerosols, there's neutral pH. So what if a negative charge COVID-19 virus come up with the negative charge membrane material? Okay, the capture efficiency is not very good at all. But most of the membrane material you can see in the market claims they have 99.9% or 99% or 95% of filtration efficiency. Okay, that is because they are not actually checking about the COVID-19 virus. And most importantly, our face masks usually not directly try to attract the COVID-19 virus. They are trying to attract our aerosols, which can have the dipole moment of both positive charge and negative charge. So it will try to attract the positive charge side of the large droplets. So it would be deposit onto the instead of directly attract the virus. On the other hand, such negative charge, because we add it to the membrane materials, it would try to decay over time. When we try to treat it by heat or by high humidity, the charge would decay. So it will, to us, I would make a precautions to the people that don't try to keep too much of the face mask, because the materials, the membrane materials, for long storage, the charges will be decay and the trapping efficiency will be lower. And so membrane material at all is still good, but it's not very good for COVID-19. It's trying to trap particles. It's trying to trap aerosols. Okay, but if it's just deal with a dried COVID-19 particles, it will be not in a good way to trap it. And here's the diagram to show how to make the membrane material. Okay, it using the normal molding machines to grow those fibers, and after that they would pass through a high voltage part that will have the corona charges to make the material being charged. So in the market, you will see, okay, just like Dr. Weller said, you got lots of different types of face masks. Okay, for medical masks, for the ordinary medical masks, okay, we already have something claim that they are ASTM F21000s, or they would claim in the European standards EN 14683. Okay, they have type 1, type 2, type 2R. Okay, actually they are the same, but they are just different standards. The code are different. Most importantly, you have to focus to the part of the BFE, okay, which is the bacterial filtration efficiency, because this kind of mask, when they launch to the market, they only do 2 tests at all. One is the PFE, we call that particle filtration efficiency, whereas another test is the bacterial filtration efficiency. Normally, most of the medical masks you can buy in the market already can achieve 95% plus. But how come you would say you would like to wear an N95 or what we call the FFP3 type of face mask? Because they have difference. Okay, what are the difference? Okay, you can see from this diagram, when we talk about the ASTM F21200 and also the EN 1463 standards, okay, they normally deal with materials that with the size of 3 microns above, okay? So that's fine for the aerosols because, as I said, most of the aerosol we deal with is between 4 to 8 microns. So it is fine if we just deal with aerosols, okay? It's totally fine. It will try to give you 95% of protections, but it won't, but apart from the ASTM, they got a requirements that of 0.1 microns. The European types don't have much data about the 0.1 micron size of materials, okay? So you might not be able to trap more smaller particles, okay? And for the Melbourne material, one of the drawback is not the 0.1 micron, but the size of 0.3 microns, okay, 0.3 microns. Because you will see in the next slides that, in the next few slides that at 0.3 microns, the trapping efficiency will suddenly drop, okay? When it below 0.3 to 0.1, the efficiency would be increased back, but it is a V-shaped efficiency. Whereas at 0.3 microns, the trapping efficiency suddenly drop for all type of this kind of filters. Whereas for higher than 0.3 microns up to a few microns, the trapping efficiency is nice for every kind, no matter it's N95 or surgical mask. But surgical masks usually don't deal with smaller size particles. And respirator masks like the N95 or what we call the FFP3, okay, they can deal with the smaller particle, especially for those in 0.3 micron in size. So if we try to buy a N95 mask, the key features of it is it can try to trap smaller particulates. This is especially important if the aerosols, because when the aerosols generate just from the exhale of our mouth, it's totally fine because it's 4 to 8 microns. But as the time it travels through the air, the droplet will be dry off. Okay, just in a few seconds, it will dry off. And when it dry off, the size will be decreased significantly. And that might affect the trapping efficiency by the face mask. So this is what I have done previously, I think 2 years ago, okay, 2020. We have tried to test different type of face masks, okay, no matter they are reusable or one time, okay, N95 or another surgical mask, okay. Most of them are good, have the filtration efficiency of over 95%. But some of them may not be that good, okay. On the other hand, look at these photos, okay. What you will see is that even though we try to select a mask that theoretically can protect from you, but you have to consider when you try to fit a mask, okay. Look at this diagram, you will see the mask is actually not very fit at all. And in fact, this mask, when our chief executive wearing this mask, okay, it's oversized and air will leak through the gap at the side, and that would not give her the maximum protections that an N95 should have. So when you try to buy a particular respirator type mask, for example, N95, many of them would have the size for your choice. And you have to take a look on how fit you need, okay? Usually you have to measure it from your nose, okay, to the chin for the distance. And you might try to fit in the mask by using different size and then to see what size that fits you, okay? But as Dr. Weller said, different masks may have different geometry and shapes. And so different brand of masks, you have to try it yourselves. Here's another very funny studies that done by Cambridge, okay? Previously published. And they say that's when you try to wearing masks, okay, you can try to fit it in by make it fit by using a lady pantyhose, okay. If you try to take a look onto the headings, okay, you will be cheated because you will think that no matter what, I just wearing a pantyhose to cover the mask, and then it will try to make sure that it fits at all and it will be fine. But actually, when you take a look onto the data, it's not, okay? When you see to the data, you can only see that only one occasions, only one of the masks that they use together with the pantyhose will have an extraordinary performance. But for other masks, okay, if you see it from the blend A of the face mask, only one of the samples would give an extraordinary performance, but other are the same or not significant changes. Okay, so whether it fits, you might need to do it by yourselves to use the pressure test, like the negative pressure or positive pressures. Try to fit it before you try using. Okay, that's about the face mask. Face masks usually use the Melbourne materials in 99% of the face mask in the markets. How about apart from the face mask, what kind of air filter we would face? The other type is our air conditioning systems. If you take a look to the air filtration systems, our air conditioning system, most of them would have the air filters. And the air filters, the most sophisticated or most reliable air filter in the market is called the HEPA filter. We call it high efficiency particulate air technology, which try to which is designed very similar to that of the Melbourne materials, okay? But the only difference is they don't have charge. They just make it just like a sieve, a mechanical sieve. And that sieve is trying to filter off air particulates that with the size bigger than the sieve. So to make it more reliable, the manufacturer would try to make the mask with smaller size, okay? Make it more dense, and so it would try to trap the particulate or virus or bacteria in the particulates in a higher percentage, okay, of that, okay? And because it's a sieve, it would only have these 4 types of occasions that it can trap the particles, no matter sieving, no matter inertial impactance, interceptions, or for smaller particles, it would have the Brownian motions. And from the yellow diagram, you can see that this is the size performance. You can see that over 1 micron, the trapping efficiency is good, and lower than 0.1 micron, the trapping efficiency also good because they have the Brownian motions diffusions scenario, and also the impaction or inertia scenario for smaller and larger sizes respectively. But in the middle size, in between 0.1 to 0.3, the trapping efficiency was starting to drop to only around 60%. Okay, that is the loophole for the HEPA filter. Okay, and if it's most difficult to deal with. This is the size that the HEPA filter most difficult to deal with. Okay, and you might ask the questions: how occasions that a filter would have or the air filter would affect us. Okay, and here is one of the study. Okay, it's not 2002, it's 2020. Okay, that is a study by a team called OWN. Okay, they try to study some healthcare workers in hospital and working environments. They try to take some of the PPE, okay, like the protective clothing, like the face mask, like the face shield from the hospital staff, and try to do this screening test, try to do the swab tests to see how much of the virus retain onto their PPE. And surprisingly, they found on the PPE were negative for those practitioners. But on the other hand, when they tried to do samples of the air outlets from the exhaust fan, they found the result is positive. That means the aerosols, when it exhales from the patients, would have a higher chance being dragged out or by the air current of the room to be transmitted through the air. So airborne transmission, in fact, after several studies done by the scientists, we found that it may be possible, at least talk about a short length, like a few meters. So you can see from the government announcement every day, previously they talk about each case. Sometimes it might have chance that the particularly would propagate through a distance. Okay, maybe because of the air filtrations, they do propagate the virus. And because of that, the US government, just a few days ago, they tried to launch a new bills of a campaign that tried to invest, okay, try to provide $350 billion to the state and local government, try to support, try to improve the current ventilations. What they are going to improve is trying to improve by using a higher levels of air filters in the air conditioning systems. So air conditioning systems is actually one of the possible source of propagating of the COVID-19 or other kind of infectious disease. And here is the chart that's what kind of the air filters. Okay, normally before this before this U.S. campaign, most of the U.S. Government buildings or they use a MERV rating number 8 filters in the air conditioning systems, which means they can try to trap breathable aerosols with the size from 3 to 10 sizes, microns, okay, with a efficiency of around 85%. But right now, after the build, they would try to upgrade the existing systems and try to implement the MERV rating from number 8 to somehow number 13. Okay, number 13, apart from just trying to trap a higher efficiency between the the breathable aerosols between 3 to 10 microns, they also try to have a better trapping efficiency below 3 microns, which is smaller in size. Another problems by our existing filtration air filters or our face masks is the propagation or the proliferations or overloading of the filters. Okay, most of the people, I understand that they would wear a mask. Once of the mask will wear for a whole day, and so you would try to the face mask already arrests a number of virus or bacteria, no matter from the external source or from your cells. And what we have found is that for bacteria, when they have been trapped by the filters, it would try to propagate, it will proliferate by themselves. And for virus, okay, if you are exposed in a high dosage of virus, those virus, after being trapped by the filters for a period of time, they might be released by the overloading of your filters, and it might escape out to the filtered air, and that might increase the chance of the risk of infections. And so people, when they are dealing with the air conditioning system, they already know such a problem, and usually they would try to do some things to prevent the filter being overloaded, okay, or to extend the lifetime of the filters. What they would use is they would try to install a UV light after the filtration systems, okay? But to my opinion, that it is not very efficient because it's in other the inactive way, microorganism or coronavirus, it takes a long time. For example, for UVC light, it's effective to kill coronavirus, but it takes 25 minutes to kill 99.9% of the virus. So, but when you think about in an air conditioning systems, the air particles, when they escape out from the filter bed to the exhaust of the aircon systems, it's just within 1 second. So it's not enough time for the UV light to kill the virus. And moreover, it would consume more energy, consume more electricity. And another drawback is like this, okay? This is one of the filter bed we found from a local shopping mall, okay? It is a famous shopping mall. And what you see is that the filter bed, after irradiated by the UV lights, just within 1 month time, the bed already being degraded by the UV lights, and it's exposed all those particles out. And the filter is in fact didn't have any functions. So what we are going to do is, what my group is doing is, 2 years ago, a guy come to me and he got an idea. His idea is that because we understand the virus is negative in charge, so by the use of the membrane material, it might not be sufficient to trap the virus if they are dry off in the aerosols. And so what to do is, how if we try to use a positive materials? And so he proposed the use of a polymers to coat onto a fabric material to make a filters. And at the time, 2 years ago, we understand that the membrane material is shortage over the market or outside the markets, and you need to pay a lot of money to buy the membrane material. And he tried to provide a solution that can do both the arrest. And surprisingly, apart from just arrest the virus or bacteria, we also found it's effective to inactivate and to kill the bacteria and virus. And that is what we found during these 2 years of tests. And here is the technology, okay? The company is called the C-Polar. Okay, you might not heard about this company because it's just a very small company. And what they do is trying to add some of the polymers, to coat some of the polymers onto the fibers of a cotton fiber, a fabric materials. We try to coat a layer of positive polar plastic onto that, and surprisingly, we found that it got a high density of polar positive polar charge density at the fabric materials, and that positive polar can help to arrest and eliminate the virus and bacteria. And what we done at the time, 2 years ago, they tell me that they have an idea and asked me to build a facility, because 2 years ago in Hong Kong, there's no such a facility to test of the face mask. And we try to set up the first bacterial filtration efficiency set up in the Metropolitan University. And what we have done is the results from that polar fabrics is very surprisingly, okay? You can see from this diagram, we have 2 agar plates, and the dot on the agar plate in the left-hand side is the bacteria, okay? We try to spray an aerosol. We try to use a nebulizer to spray an aerosols. And if we do not have the filters, you can see all the colonies can be deposited onto the agar plate, and it's growing nicely. But after we have placed the filter onto that, none of the colonies will penetrate through the filters, and all of them being arrested. And the results from us, also from other laboratory, confirm that the material can have a filtration efficiency over 99.9% for bacteria. Apart from bacteria, we also interested in how it deals with virus, especially the coronavirus. So we have sent the materials to a laboratory in Finland, and they have done 2 tests. One is using human coronavirus, and the other is called the Coxsackie virus, which is the one who very difficult to deal with. And here, what we have seen is that apart from just being filtered off, it also have a very good performance to inactivate. You can see that in the early beginning, we tried to input at around 50,000 copies of virus. But after 5 minutes time, we found that only a few copies of the RNA still remaining. Okay, this diagram is plotted in a log size, so in a log scale. So what you can see here is actually more than 99.5 not filtration efficiency, but also the inactivation efficiency of the coronavirus and also the Coxsackie virus. And in our lab, we also deal with the bacteria. We try using different types of pathogenic bacteria, and the result is very good. That it can inactivate more than 5 logs. Okay, that means 99.999% of the bacteria by the use of the filters. Okay, what we done is can shown in the diagrams here. Here are 2 plates. What we did is we tried to splat the plates with bacteria, and then we dip the disc with the filter materials. On the left-hand side is just a normal membrane material. It attracts some of the bacteria, and then you can see the dense. You can merely see a circle, whereas inside the circle you can still see a lot of colonies remaining. But on the other hand, for the use of the C-polar, the positive polar filters, you can see a clear zone found. Whereas the material not just arrest the bacteria, but also inactivate, because afterwards we try to use saline to try to rinse off all the bacteria from the filters, and we found nothing. And some of the people might concern about the filter. Would it release any chemicals to that may have a toxic effect to the human when we're wearing it every day? So we done a cytotoxicity studies by the use of nasopharyngeal epithelial cells. Okay, and the results shown in this diagram is that no matter it's cold or non-coated fabric materials, it didn't have any toxic effect at all to the human's epithelial cells. That means it's not cytotoxic. And because of that, we can confirm that we can use it safely. And all the tasks we did in the laboratory, we tried to see how it inactivate bacteria, how it filtrate bacteria, which is in a lab settings. But in fact, we have done trial one beforehand, a few months ago. We done a trial one of the air filters by putting the air filter in a buildings, okay, called the ICC, the International Commerce Center, and in the West Kowloon. And what we did, we fit in the filters with the C-polar, and one of the control is the normal filter. And afterwards, after 1 month, we take it out and try to see how much antimicrobial properties it have. You can still see the one with C-polar technology, they still have the antimicrobial properties that none of the colonies will be remaining after the incubations. Whereas the traditional HEPA filter, you will see that a bloom of bacterial count of 125,000 colonies will be formed in the filter. Okay, and so you can see the difference. And if we can use this kind of technology in the air filtration units, it will try not just try to arrest all the bacteria and let them grow into the fibers of the filter, but it also try to kill it, so that it is a very good solution to decontaminate some of the area, especially in the clinic or in the hospital settings. And we also comparing the test results. We also done some of the test results in other universities, and they did try using the COVID-19 virus, and the result found that in a wind tunnel test using a high speed of air flow, it can still find the reductions of the COVID-19 virus is still very promising. It can have at around 99.3% in a high speed, high flow filtering systems, whereas the pressure drop of the filters is relatively low comparing with the US standards. And what's the implication of the low pressure drop is when a filter is placed into the air conditioning system, the pressure drop will make the blower need to blow more air to get through the filters so that it can filter off and going into the to the working environment or to the other places. That means you need more energy if the pressure drop is high. And if the pressure drop is low for a filter material, it can in fact not just helping you to make the cleaner air, but also try to save your money. And one of our collaborators is the Harvard Medical Schools, and they also did the same similar test of the bacteria, and they do it into a treated textile materials, and they also found the material with the polymer polymers can effectively inactivate bacteria and also other pathogens. And recently, the company already got the exemption, the emergency exemptions from the US EPA that can be used for air filtration units, okay, for the aircon systems. On the other hand, for the face mask, this company, the C-polar material, already being adopted by the UK NHS. They use it to manufacturing their FFP3 masks. Okay, the NHS actually they build a manufacturing facilities in UK, try to manufacturing the masks themselves, but the filter material they use is made in Hong Kong. Last week, okay, from the press release from the Hang Lung Properties, okay, they have announced the use of these filter materials for use in their buildings. Okay, they in their annual report they claim that they got quite a number of tenants with a clinic or healthcare centers, and that installation of this kind of filters can actually helping them to make a more hygiene environment. And here are our research collaborators. Apart from the Hong Kong Metropolitan University, we focus on the bacterial testings of the antimicrobial filters. Also, we also collaborate with other universities like the Harvard Medical School, University of Minnesota's Mayo Clinic, Johns Hopkins Universities, and all of them in this project. Okay, that's the end of my presentation. Thank you very much. See if you have any questions.
Okay, thank you for Dr. Alex's very informative presentation. I actually know much more about the mechanism of filtration for the mask and the respirator that I use every day. Dear members, here come to the Q&A session. Is there any question from the floor?
Yeah, I have got a questions for Eric. Yeah, I noticed that during your presentation, you mentioned that the fabric material, which is quite easily can be able to install it in the air ventilation system. Yeah, and do you think that do we need to change quite frequently, because as the we all know that in the air conditioners, it is quite easy for this to trap dust and dirt over those areas, and you usually use the cleaner maybe once for every 2 or 3 months, yeah, to get it clean. Can this fabric just be washed as the filters, or maybe that you have to dispose it of before that and install a new one for it to get full function?
Yeah, I'm not an air conditioning guy, but I can based on the counterpart, the C-Polar Biotech Limited, they keen on doing the air conditioning system. They right now they got most of the products are in this for the centralized air conditioning systems. Okay, they got the filters that exactly the same as the use in the shopping mall or centralized air conditioning units. They give us the information is that the frequency to change is around 6 months for this kind of products. But I think they might try to explore the markets, like in the clinic. I understand some of you might use the air conditioning machines that we use at home, and we got the filters at the outlets of at the inlet of the air conditioning systems, and it's just a piece of cloth. And previously we done some experiments. We tried making some reusable face masks by dipping the polymers onto a cotton cloth, and the result is good. And what we did is we tried to wash it for 60 times, just like we did for the copper filter by the given by the government, and the efficiency is still there, still over 99% after 60 times of washing. So maybe the CPRO might consider to have some kind of that kind of filter cloth that you can install into the air conditioning system at home or at some of the clinics, and you might need to just take it out with your protective clothing, wash it, and then clean it, and then put it back to the aircon system, and it functions again. Maybe a few times you can wash. But our experience is for those air conditioning systems centralized, the big HEPA filter-like filters, they claim that the lifetime is around 6 months. And so normally those developers or those shopping malls, right now they start using this kind of air filter, and every year they just change by 2 times. Okay, it's quite not very expensive one. In fact, to my understanding, it's not very expensive.
I think this is a very good news, yeah, because seem to be that it's not because in Hong Kong the problem is that if we want our air to be clean, yeah, there's two ways to do it. It's either by filtration. Another method is by dilution. But the problem of the dilution is not very good in Hong Kong because the air outside may be not as good as expected. Yeah, therefore, seems to be the more straightforward way is that we can do the air filtration. If we can install this kind of air filter in our air ventilation system, actually it will quite simplify a lot of mechanical installations and things like that. Yeah, because what most of our colleagues are doing now is that they buy those HEPA filters, yeah, so that they help to clean the air inside the room. And then, however, those filters need to be changed maybe every 6 months. I think this is a quite reasonable time, yeah. And then to make sure that the air filter is functioning properly, yeah. But if it can be installed in the air conditioning of the system, it will be even better. And it is good to know that those shopping malls and those big commercial buildings are more keen to use this kind of filters to help to improve the air quality. Yeah, this is something is a good news here.
Is there any more question? Any question from Paul? No. Michael. Okay. If there's no more question, that ends the webinar tonight. Thank you, Dr. C. Thank you so much.
Thank you very much. Thank you for the invitations.
Thank you.
Thank you.
Thank you.